we exist, because we need water to be a liquid. Alright, so this next one, kind of odd. So it's induced dipole forces. So if you think about the word induced, the only place I ever think about it is with labor, and it means we force it to happen. So induced dipole means it's kind of forced to happen. And so there's a couple ways that an electron cloud can be forced to happen. The main way, if you think about if you have something nonpolar, let's say a Br with a Br, and we've got electrons on both sides, and nobody's really getting more than the other side. This is nonpolar. There's no side that's different. But let's say that we brought in an Na+. Okay, so there are electrons floating around both the bromine atoms. There are electrons, the 1s2, 2s2, all those electrons are sitting there, whatever. And so these are our shared electrons. But what this plus is going to do is it's going to attract the electrons. So it's going to drag the electrons towards this side. Even though the Br and the Br, there's nobody necessarily winning in that war for electrons, the Na plus is going to induce this to become a polar molecule. It's going to pull those electrons over toward it and make this partially negative, and which would leave that partially positive because the electrons just went were attracted to the Na plus. So that's pretty much how an induced dipole happens. The other way that and that doesn't happen permanently. Let's say you remove that Na plus. Do you think that the partial negative and partial positive stay? Well, no, there's no reason for them now. There's no reason that this Br is any less attractive than this Br for those electrons. So it returns back into its normal state. So you have to induce it. You have to force it. It's a distortion. So this will also happen just naturally all on its own. And so if you have just a Br just sitting all by itself, no, two Br, sorry, a Br2 by itself, there are electrons whizzing around here, and they're in constant motion. So if you think about, let's take a ship, and we've got people all over it, our crew members, and let's say they're just whizzing about doing their duties. At any one moment, because they're just moving about randomly, independent of each other, right, we could end up with, let's say, all three of these workers on the same side. Well, what that's going to do to your ship is kind of tilt it. It makes it heavy this side and light this side. Well, you can fix that. It's not permanent. If you move this guy back over to the other side, and this guy back to the middle, it goes back to being pretty much even, and there goes your imbalance. And so the same thing happens with the bromine. Well, let's say these electrons moving about, and we have the bonded orbitals right here in between. They just, for one instant end up over here. Just an overload of them end up on one side. Well, that leaves that partially negative and that partially positive. Well, the electrons keep moving. They don't stick over there, and they eventually go back, and there goes the dipole disappears. But what can happen is, let's say we had another Br2. Okay, and so it's sitting here, and it's nonpolar as well. But this guy right here just has an imbalance of electrons just instantaneously and ends up partially negative and this side partially positive. Well, if this thing right here is sitting next to it and it's got its perfectly little balanced electrons, what's this partially negative instant going to do to it? Well, it's going to make that partially positive. Okay? It's going to push those electrons that were here toward that direction, push them away, because this guy's negative. There's already an overload of electrons here, which makes that partially negative. And so it kind of induces a whole polarity, but it doesn't last. It's instantaneous, and then it goes back. And so these things can happen with nonpolar molecules. They can also happen with polar molecules. It just makes it more negative than it already would have been. And so for a nonpolar molecule, this distortion, this overload, it results in a temporary induced dipole moment. Temporary is key. It goes back. and then this happens again. It happens instantaneously, millions and millions and millions of times, and then it's a constant motion. Okay, if it's already a polar molecule, this still happens. There can be an overload. Okay, it just makes the dipole moment a little bit stronger for that instance. Okay, if you had HF, where this side's already partially negative, and this side's already partially positive, and just, okay, and this is not a great example because there's not that many electrons, but let's say the electrons that are shared and whizzing about end up just overloading this side and making it extra negative, okay, and then makes it even extra positive. Well, then they go back and it just makes this a little bit stronger, and then they go back and it returns to its original polarity. So it's just a temporary enhancement if it's polar, or a temporary polar dipole moment if it's not. So we're going to go back to the ship metaphor. So if we've got 3 little workers on our whole ship, and they all end up one side, yeah, it's going to dip down a little bit that way and rise a little bit this way. But if you've got 3 workers on a ship, it's probably not going to affect it that dramatically much. Okay? I mean, it's not going to be that far of a drop down here and that high of a lift up here. But let's say you've got 200 of these workers. And I'm not going to draw 200. But just to give you an idea of the size, let's say we've got all these guys, and yeah, oops, they all ended up on top of each other on the very end of this ship. Well, that's just going to drag that down all that more and lift that side up all that more. And so how this relates to these atoms is, these guys are electrons that are moving. And so a phrase that you've got to know is called polarizability, the ability to become polar. So the more electrons you have, the more likely it is that you're going to end up with an overload on one side that's going to cause a distinct negative, or a deficiency on the other side that's going to cause a distinct positive. If you've only got 2 electrons, yeah, okay, the 2 are on one side, all right, that's probably likely, but they're not going to cause that big of a dip as far as being partially negative or partially positive. And so you've got to know that polarizability goes up as electrons go up. As the number of electrons go up, the more likely it is that they're going to have an overload that matters, that's going to cause a positive or negative. And so, just to show you a comparison, if we took Br negative, or Br2, and then I2 with each other, there are electrons around I2, just like Br, but each Br has, let's look it up, a certain number of electrons. Alright, each Br has 35 electrons, each one of these. Each I has 53 electrons. And so, in the run of play, basically, in the constant motion that electrons are having, there is a possibility, a very slim, but there's a possibility that all 70 electrons will end up over here. So you've got 70 electrons and no electrons. Alright, so that's obviously very, very negative. Not likely that all the electrons are going to end up on one side, but let's say that happens. Well, down here for iodine, there's also a slim chance that all 106 electrons end up over here and leave this very negative. Well, if you look at between the 2 of them, this is a whole lot more negative than this is. Okay? And so if you were going to induce a dipole, let's say that with this other negative, this is now very positive, okay? If you're going to put another I next to it, this is a whole lot more positive than this bromine is, which is going to force this guy to be a whole lot more negative, and it'll carry out in that kind of chain reaction. But the more electrons you have, the more polarizable it is. And so the other thing that goes along with the polarizable is not all 70 electrons or 106 electrons are going to end up on one side, but the ability for the electrons to move to one side is also dependent on how far away they are from this very possessive nucleus sitting in here. Okay, that nucleus is in the center, it's got these electrons around and around and around. Well, not only does iodine have more electrons, its electrons are actually a lot further from the nucleus than bromines are. It's a lot bigger atom. Those electrons are down in, I think, 5p, maybe 6p, whereas bromines are in 4 or 5p. So these electrons are a lot further, which enables them to move a lot more freely than bromines would. Bromine would keep track of those a little bit better. And the same goes on up the periodic table. So that's what induced dipole forces are. About as clear as mud right now. So here's just an image of what I kind of drew before. So if you had no dipole, completely spherical, whatever it was, if you put a positive cation up next to it, it would force the electrons to become attracted to it. And so that would make that partially negative and partially positive. So that's called an ion-induced dipole, because the ion is forcing that polarity. And then when you take the ion away, that polarity disappears and it goes back to being the nonpolar. The other thing you could get is, again, you have no dipole, spherical atom, and you put something polar up next to it. So here's water. It's negative here and positive over here. And so again, if this negative approaches, it's going to push the negatives that way. And so it's going to make this side partially positive and that side partially negative. And so now you've got a dipole-induced dipole. So it's a polar molecule forcing this nonpolar to become polar. Alright, and so I already kind of talked about these, but London dispersion forces are really, really important, and I've already explained them, but not as this name. And so they're named after the German physicist. But what they are is those momentary oscillations of electrons, the overload. It is the instantaneous dipole that happens when you have an overload of electrons on one side. And so what's really key here on it is that these are weak because they happen because you have a slight overload and they're instantaneous and they go away. But the key is any particle at all can exhibit these. Everything has London dispersion forces because everything can accidentally have all the electrons on one side or a little bit of an overload of electrons. Right? And so the dispersion forces are pretty much the dominant force between identical molecules like Br2 and another Br2. There's no side that's any different than anything else. And so the only way these things are going to be attracted to each other is if they, that side's negative and that side's positive just for an instant, which would then force, if this guy were sitting right here, it would force chain reaction, that side to become partially positive and that side to become partially negative, and now those are slightly attracted. But that's not going to exist forever. That's going to go, the dipole that happened is going to go right back, and that's going to disappear. But the key for this is we talked about the more electrons you have, the more likely you're going to have an overload on one side, and if you have more electrons, they're generally farther from the nucleus. And so if you have the iodines, there can be a partially negative side, let's say, but because iodine has more electrons, its partial negative is going to be a bigger deal, a larger negative, than bromines. So that would cause this to be a partially positive and partially negative. That would cause this to be a bigger partial positive and bigger partial negative. So the question, though, is how are these two molecules going to stick together? Well, because these are not as positive or not as negative, this is going to be weaker than this. Solely because that's going to be a stronger negative and that's going to be a stronger positive because there are more electrons. And the phrase is the iodine is more polarizable. It has a larger ability to become polarized. So it's got to do with the number of electrons. And so the key with this is that if you look, if this is weaker and this is stronger, if you asked about states of matter, okay, we've actually talked about that Br2 is actually a liquid on the periodic table. It's one of our two liquids. I2 actually comes naturally as a solid. And that's because that is a stronger connection than the Brs with the Brs. And so that's what's controlling whether they're solid, liquid, or gas. So just to show you, you know that Cl2 is a gas at room temperature, and so these are nonpolar as well, but we can have the same partial positive and partial negative. But because there are less electrons in Cl, that's going to be even smaller positive, smaller negative, smaller positive, smaller negative. And so that's going to be the weakest, because those are not very polar, because Cl negative has less electrons than either Br or I, and so it is not as polarizable, not able to become as polar, so the intermolecular force between them is weaker. So that right there, that is the London dispersion force. Okay, and so the strength of these is directly related to the state of matter. And so you got to look at the number of electrons, and then the other thing you have to look at for London dispersion forces is the shape of the molecule. We've talked about shapes for polarity, but shapes that allow more points of contact over which the electron clouds can be distorted, so the positive and negatives, the more those things can actually stick together if they have partially positive and partially negative, the stronger the attractions are going to be. So I want you to think about it this way. On the shapes, if we have a sphere here and a sphere here, the most they can touch each other is right in there. But if you have a line here, okay, or let's make it just a rectangle there, and we have another rectangle there, they can actually be attracted and touch each other all along this connection. So they're able to form these intermolecular connections all the way across. Whereas two spheres, that's the only intermolecular force right there. So if that's all you've got, that's going to be easier to break probably than all of these connections that happen over and over and over. So that's what the shapes are. More points of contact, the more positives and negatives that can actually touch each other. Okay? So this is, I guess, a more official drawing of London dispersion forces. These are two hydrogen molecules. And so just randomly an instantaneous dipole, electrons end up heavily weighted over here. So that means that they're not over here, which makes that partially positive. Well, that's going to attract the electrons that way and make this guy partially negative, this guy partially positive, and they're going to then want to stick together because that's partially positive and partially negative. So we know a little something about H2. H2 is a gas at room temperature. So what does that tell us about the strength of that attraction? This is very, very weak. And so we ask ourselves, why is that so weak? Well, hydrogen only has 2 electrons in the H2. It only has 2 electrons total. That's not all that polarizable. So sitting here, there's only 2 electrons. That's not much of an overload here. And so that's a very weak positive and a very weak negative, which is a very weak attraction. Alright, so just to show you again about the actual bonds, those are the connections. This is actually between the Na and the Cl that's over and over and over. Okay, we have that large covalent that's actually sitting in here. That's that thing right here. That is not what breaks when this becomes a gas. The intermolecular force is the weak thing in between two. But this guy right here is the covalent, right in there. And then metallic is between irons with all the positives, and then the electron C floating around. So if you look at the numbers here, and we're going to go look at how strong intermolecular forces are. Okay, and so here we go. If you look at these ranges, okay, if you think back to the table that I just showed, those are, the lowest is sitting at 75. Whereas intermolecular forces, the strongest they can become is between an ion and a polar molecule. Okay, well that involves ions. The next is hydrogen bonding, just a very special polar to polar, okay, like a water to a water. Then we have polar to polar, plain polar to polar, not special like hydrogen bonding. That's even weaker. Okay, that's ICL to ICL, the 2 polars. Then we have ion-induced dipole, so that's an ion forcing a non-polar. Okay, so induced dipole means non-polar, but it's forced to become polar because of the ion. Okay, so if we put a plus up next to the oxygen molecule, that's going to cause a 2 plus. We have the oxygen molecule. that's going to cause the electrons to be attracted this way, toward that positive. So that ends up as partially negative and partially positive. So it's about those sticking together. And then we got dipole-induced dipole, so something that's polar, like HCl, which we know that side's negative and that side's positive. If it's sitting next to Cl2, well, that's nonpolar, but that negative right here is going to force the electrons to go away from it, leaving that partially positive and that partially negative. And now those are attracted to each other. And then the last one, the weakest, is London dispersion. Okay, so between the F's, and all this is randomly polarized. Okay, let's say this side ends up as negative, just randomly. Well, that's going to draw the electrons toward that direction, leaving that partially positive and partially negative. Sorry, should be negative. So it's that weak attraction that's not going to last for a long time. So I want you to pay attention to this number, that it's very weak, but if you look at what it can do, it can kind of rival the hydrogen bond or the ion dipole. This is dependent on how many of these polarizability, how many of these overloads can happen, and how big that polarizability is. So is this a big negative or a small negative? So we know that water can hydrogen bond and is a liquid at room temperature. Iodine is nonpolar, but is a solid at room temperature. So this guy, even though it only has London dispersion, which you're allowed to shortcut LDF, this guy has hydrogen bonding. This is supposed to be stronger, but obviously this guy is stronger because it made it a solid. They're really close and attached to each other. And so it matters on the ability of the polarizable cloud. Iodine has a ton of electrons. And so that allows it to be a lot stronger when it does this random overload than it would be if it only had 2 electrons like hydrogen. So what you have to look out for in London dispersion forces is all molecules do this, and it's based on electrons and shape. And so it can overcome any of these if there's enough of them. And so that's where you're not necessarily going to have to be able to predict that, but you have to explain when they tell you this is a solid, this is a liquid, explain why. Alright, so what we're going to try to do is identify the type of molecular force, the dominant intermolecular force, and we're also going to select the substance that we think has the higher boiling point. Okay, so we have ionic, which is kind of weird because it's not really an intermolecular force, but it is what you have to separate to boil it. And then we have ion dipole. Then we have hydrogen bonding, which is just special dipole-dipole. And then we have all of the induced dipoles. Okay, so I'm just going to use just plain induced dipole, which is London dispersion forces. Alright, so we're going to pick the substance with the higher boiling point. That doesn't mean we're mixing these two things together. We're picking, is it harder to separate MgCl2 from another MgCl2? Or is it harder to separate one PCl3 from another PCl3? Alright, so let's look at MgCl2. What is this? Well, this right here is an ionic compound. So it doesn't really exist as an MgCl2 attached to another MgCl2. This is bad. It actually exists as that lattice structure with the Mg2 plus and Cl's. Okay, and then another Cl here, and we've got another Mg2 plus. So we've got a lattice structure over and over and over. It's going to be very hard to break. Any of these, the more attachments they have, the harder they are to break apart. Okay, and then we have this is covalent for sure, right? But that is an intramolecular force, so that doesn't help us on boiling point. So we've got to look at it. PCl3. Okay, to figure intra, we've got to look at more than one of them. Alright, so if we look at this right here, these molecules, they'll say, okay, covalent, we gotta know, is it polar or is it non-polar? Because these three involve polar molecules, and this guy involves non-polar molecules. Alright, so this guy's definitely polar because it's not symmetrical. That has a lone pair of electrons. There's a net dipole moment. So this is polar, so we have some options. Is this polar with another polar, or is it a hydrogen bond, special case, or is it ion with a dipole? Well, the only way you have ion with a dipole is if you have two different things. Right? You have to have an ionic compound and a polar compound. Well, these are just both covalent. So we're not going to have any of that. Can this hydrogen bond? There's no hydrogens in it. So we're just going dipole, dipole. And so we got to ask ourselves, okay, so what's the force between these two? It's going to be dipole, dipole. And then we've got to ask which is stronger, ionic or dipole, dipole. Well, it's going to be ionic, so that one's going to have a higher boiling point. It's going to be harder to rip it apart. That's all that we're talking about with higher boiling point. Harder to rip the different things apart from each other. Alright, so I also want you to know that even though this is polar, it also has LDF, because everything has LDF. It's just an oopsie with the electrons overload. Alright? So you gotta look out for ionic. Ionic kind of is the king. It kind of trumps everybody. It's not really an intermolecular, it's kind of different that way. The other thing with ionic is you gotta look for network covalent. That's covalent compounds kind of acting like ionic. So we've got CH3, or NH2, so I'm going to draw that, CH3, NH2. Alright, so we've got to draw another one if we're going to do inter. Sorry. Alright, and let's go through the list. Ionic or covalent. These are covalent because they're not ionic. It's not a metal and a non-metal. And so covalent doesn't tell us anything about intermolecular forces. So then we have to ask ourselves polar or non-polar. Well, it's not symmetrical, and we're going to have these lone pairs of electrons, so these are definitely polar. Then we ask ourselves, in our polar section, is it capable of hydrogen bonding? Do we have hydrogens attached to an H, or an F, N, or O? Those two definitely are. So it's going to hydrogen bond. So that makes that partially negative and partially positive. So this is capable right here of hydrogen bonding. Okay, so then how this would attract each other is that right there would be attracted to the negative there. And then these positives would be attracted over the negative. So there's our H bond. Alright, so that is a particularly strong kind of dipole-dipole. So then we're going to look at CH3F, CH3F. And we got to draw two of them for inter. Alright, so then we have to ask ourselves, ionic or covalent? These are covalent, but that doesn't tell us inter. So we ask ourselves polar or non-polar. Well, these are polar, with this side being negative and this whole blob being partial positive. Okay, and so then we ask ourselves, can it hydrogen bond? Does it have a special case? Well, there's no H attached to an F, N, or O, so it cannot hydrogen bond. So that means it's just going to be dipole-dipole. So if you were asked to pick which one has the higher boiling point, we're going to go with the hydrogen bonding as stronger. The other thing I need to add in now is both of these have LDF. And so the LDFs, you're like, well, they both have them, so it kind of cancels it out always. That's not always true. Some LDFs can be stronger than others, and what you look at for this is the number of electrons involved. And so if you look at this formula, okay, I'm going to get rid of, if we're counting up total number of electrons, both of these have a CH3. So I'm going to cross those out. And look, and nitrogen has 7 electrons plus 2, so that's 9. And fluorine also has 9. So their LDFs are equal. And if you got confused by me crossing out the CH3, C's bring 4 and H's bring 1 each, so I was just saying those numbers are going to be the same. And so both of these have the exact same number of electrons. And actually, I was doing valence here and non-valence in the other, so this should actually be, 6? So the total number of electrons we have is identical, so the LDFs, those are the same, so those can't tell the difference. We do need to look at the difference in the LDFs. But hydrogen bonding trumps dipole-dipole when the LDFs are the same. So that one has the higher boiling point. Alright, so next one. We're going to look at methanol, so CH3OH. So CH3, and then we've got O attached to an H. And we've got to draw 2 of them for intermolecular. Alright, so we have to ask ourselves, ionic or covalent? It's covalent. Doesn't tell us inter. So we have to look, is it polar or nonpolar? It's polar because we have an asymmetry and we've got a negative sitting here. Alright, so these are polar. And then we have to ask ourselves, can it hydrogen bond? Is there an H attached to an F, N, or O? There is. So this guy can hydrogen bond. It also has LDF. And so then we have the attraction here would actually be between that positive and that negative. There's our hydrogen bond. Then we got to look at ethanol, which is CH3CH2OH, where H is. I'll draw 2 of them, so we can see inter. Alright, so again, ask ourselves the questions. This is not an ionic compound. These are polar. These have the H's attached to the O, so they can hydrogen bond. Alright, so this would be partially negative and partially negative, partially positive, partially positive. So the hydrogen bond would happen in here. Alright, so this also has LDF. So we both got hydrogen bonding. So that doesn't tell us anything, so we have to look at the LDFs. And so to do that, we're going to look at the total number of electrons. So we're going to go to the periodic table and look up the electrons. Well, carbon has 6, hydrogen has 1, so there's 3. Oxygen has 8, and hydrogen has another 1. So we have, I think, 18 electrons total. I'm not just doing the valence electrons, I'm doing all the electrons. And then I've got, again, 6 plus 3 plus another 6 plus 2 plus 8 plus 1. So I've got 9 and 8, which is 17, and 9. So I've got 26 electrons. So this guy has 18 electrons, this guy has 26 electrons. The more electrons you have, the higher the LDF are going to be because it is more polarizable. And so this one's going to have greater LDF, which is going to lead to a higher boiling point. So if you go look up methanol, and I think we did them on one of our pages, methanol versus ethanol, methanol will have a lower boiling point. I think it's somewhere around 56, where ethanol is somewhere around 78. So this one's going to have the higher boiling point. Alright? And then last one of these on this page, we got hexane, which is C6H14, and 2,2-dimethylbutane, which I also believe is C6H14, but I'll know better when I actually draw it. So here's hexane, and it's C6H14, and each one of these lines goes to an H. And then 2,2-dimethylbutane. I'm going to erase that so we can see a little bit better. Alright. Alright, I'm going to go ahead and draw the H's in on this guy. Alright, and that should be C6H14 as well. Okay, so they have the same formula. Well, what does that tell us? Okay, they both have LDF for sure, because all things do. And if they have the same formulas, they have the same electrons, which means they have the same LDFs. There's the same likelihood of electrons overloading to one side or the other. Okay, and so then we're going back to our basic questions. Ionic or covalent? These are covalent. Doesn't tell us anything yet. Polar or nonpolar? And so this guy obviously looks symmetrical. This is nonpolar. Okay, even though this guy doesn't look symmetrical, you're gonna have to kind of get in your head that hydrocarbons, just the C's and the H's, are gonna be nonpolar. Their shape's definitely gonna affect some things, but there's no H that pulls harder on the C that it's attached to. Even though it isn't particularly symmetrical, each C is attached to at least one other C and then a bunch of H's. The only complaints you could have at all for the non-symmetry is right in here, and that's going to cause our problem anyway. But this is also nonpolar. So then our only option is LDF. That's our only option for nonpolar things. Is the only way that they can attract each other is through an induced dipole. Otherwise, these two blobs are not going to be attracted to each other at all. And so I got lazy and I didn't draw a second one of these blobs. So for an intermolecular force, we would take this guy. Let's see if I can pull this off. And try to see how attracted it is to another of the same molecule. So I realize this is kind of a mess now, but what we're looking at is what are going to be the attractions between these two molecules. Well, we've said that they're nonpolar, so the only way they're going to be attracted to each other is if there's an overload of electrons, which we call London dispersion forces. But we've said, okay, alright, so those are going to be whatever they are, some weak, very weak London dispersion forces. Well, the same thing happens over here. Is if we have one of these big blobs, right, and we're trying to see how it would be attracted to another one of its same molecules. So we've got this one trying to be attracted to that one, and we've got this guy trying to be attracted to this one. Well, they both are nonpolar, they both only have LDFs. All you're going to be able to do is have an overload and have some kind of weak interaction between the two in both of these. So how do we tell the difference? Because they're definitely going to have different boiling points. This is where shape comes into play. If you have this hexane drawn like this linearly, if there's an overload, these things can interact straight up and down on a bunch of different things. If there's an overload, they can link up all along those points. And that's basically the two kind of rectangles that I drew before. They can line up all the way in between. Whereas these kind of almost end up as spheres because of the carbon groups coming out of it. And even if they overload, they're only going to be able to touch at this little small area in here between these few atoms. And so hexane is actually going to have a higher boiling point just because it has more points of contact, right? Because of its shape. Alright, so we're going to try 3 more, and then this lecture from hell will be over. Alrighty, so CH3Br and CH3F. So we're going to look at one of these. We've got to draw another one for intermolecular forces. Sorry, F. Alrighty, so we're going to have to predict higher boiling point again. So let's look at this. These are covalent again, so we have to ask ourselves polar or nonpolar. Well, we've got lone pairs. It's going to definitely be negative toward here, which is positive over here. It's Positive over here, negative over here. So we have polar. This is polar, so we have to ask ourselves, right, can it hydrogen bond? Do we have an H attached to an F, N, or O? No, so it can't hydrogen bond, so all it's got is dipole-dipole. And it also has LDF because those come with the territory. Always there. So we go over here and we ask ourselves the same question. Well, it looks almost identical, except we have an F. So we have partial negative there, partial negative here. Okay. And so there is going to be an attraction between these two right here. So we have to ask ourselves, this is polar. And can it hydrogen bond? We do not have an H attached to an F, N, or O. So it cannot hydrogen bond, so it can just dipole-dipole. And LDF, because it's always there. So then we have to ask ourselves, okay, is there any difference in these dipole-dipoles? No, they're both polar. And yes, I realize that the F will be a little bit more polar than the BR. That is a good thing to take into account. But we also have to compare their LDFs. And so if we look at CH3Br, carbon has 6, hydrogen brings 3 total, and bromine has 35. Over here, carbon has 6, hydrogen brings 3 total, fluorine has 9. So CH3Br, each one of these blobs has 44 electrons, and each one of these blobs has 18 electrons. And so, as far as their LDFs go, because we always have to compare those, because those matter, they build up, okay, who has the stronger LDFs, and it's based on their number of electrons. So this guy almost has 3 times as many electrons, about 2.5 actually. Number of electrons, this one has a much stronger LDF. So not only do they have dipole-dipole, this guy does have a little bit stronger dipole-dipole. This one has a lot stronger LDF. So I'm going to go that this one has a higher boiling point. And then I'm going to go look it up. Alright, so I looked it up, and the boiling point of the CH3F is negative 78 degrees Celsius, which means these aren't very hard to split apart. This interaction here between the positive and negatives, that's not very hard to split up. Okay, CH3Br, boiling point is 3.5 degrees Celsius. Still not as hard, but that hard to break up compared to like water, right, with our hydrogen bonding, but it's a whole lot higher than that thing. And so we get to see how LDFs actually affect things. Alright, so we got 2 more, and we're done. Alright, so C2H6, ethane or propane. So C2H6. And we got to draw another one for intermolecular forces. Alright, and then I'm going to draw propane. I'll leave off the H's because I'm tired of the H's. Alright, so we have to ask ourselves some questions. These are both covalent compounds. Okay, so ionics out. Then we have to ask ourselves, okay, polar or nonpolar? These are nonpolar, which means their only intermolecular force is LDF. Okay, and then we go over here, same thing. These are nonpolar. So their only intermolecular force is LDF. Alright, so then we've got to compare the strength of their LDF. Well, carbon brings 6, so we've got 12 electrons there, plus 6. So we've got 18 electrons from ethane. Carbon brings 6, so we've got 18 plus 8, we've got 26 electrons. So, as far as whose LDFs are stronger, they're based off of the number of electrons. So, propane's going to win on the LDF thing. So if I had to guess, I would guess that this guy has a higher boiling point. And if you look it up, it definitely does. The other thing we need to look at, that we looked at with shapes, or with nonpolars, was their shapes. Both of these have these linear structures. Nobody's in that spherical shape, so they'd be able to touch each other at the same points of contact. If you lined them up, these would work identical. So the shape doesn't play into a factor in here. Alright, so our last one looks like propanol. So we've got CH3, CH2, CH2, OH. Put lone pairs on there. So we've got to draw another one for intermolecular forces. Alright, so let's ask ourselves about this. What's going on here? They're definitely covalent compounds. That doesn't tell us anything yet. So then we got to look polar and nonpolar. This is just going to be polar. We've got an asymmetry with these lone pairs of electrons. So these are polar. So we have to ask ourselves, can this hydrogen bond? Alright, well, do we have an H attached to an O, F, or N? Yes, we do. That one right there. So this one's particularly positive, and that's particularly negative. Alright, so this one can hydrogen bond, which is just a special form of dipole-dipole, and it also has LDF. Alright, so then let's look at CH3, CH2, O, and then CH3, lone pairs, lone pairs. Let's draw another one. Alrighty, so let's look at this guy. This is definitely covalent. Not important for us here, it's just not ionic. And then polar and nonpolar, we do have an asymmetry in these lone pairs of electrons. Leave this to be partially negative and both these sides to be partially positive. Alright, so then we have to ask ourselves, is it our special kind? Is there a hydrogen bond? Is there an H directly attached to F, N, or O? No. So this cannot hydrogen bond, but it is polar. So it is going to be dipole, dipole. And we also have LDF. So we have hydrogen bonding and we have dipole-dipole. And so hydrogen bonding is stronger, but then we've got to compare their LDFs. Their LDFs definitely matter. So we do that by total number of electrons. So I'm just going to look at their formulas. I'm going to kind of sum up this formula. So this one's going to be, what, C3H8O. And this guy's going to be C3H8O. So they have the same formula, actually. So that means they're going to have same number of electrons, which is same LDF. So LDFs are not going to matter here because they're the same. So hydrogen bond is going to trump dipole-dipole. And I'm going to pick propanol to have my higher boiling point.